Here's the other plate. And we know what's going on. We have an E field that is pointing down everywhere if the top plate is positively charged and the bottom plate is negatively charged. And we know what that E field strength is, right? That E field strength is sigma over epsilon naught, right? We solved Gauss's law to figure that out. But sigma is in fact Q over A. What is the charge on that top plate? That's what the Q is. There's obviously going to be negative Q on the bottom plate. All right, what is flux? Flux is equal to that electric field times the area. If I figured out how many electric field lines are crossing that area, that's the flux inside the capacitor. Okay, well that looks pretty good, because if I multiply E by A, I'm going to get rid of that A. Let's just plug it all in. We have E, which is Q over A, and then we're still dividing by epsilon naught, and then we're going to multiply by A, and so we just end up with Q over epsilon naught. Now, we don't really know what Q is yet, but we remember that a capacitor is related to how much charge is on it and the voltage across it by this relationship right here. Q equals CV. The voltage across the capacitor multiplied by its capacitance, that tells you how much charge is on it. All right, so we can put that in right here. We've got C times VC over epsilon naught. But VC is this thing right here. So this becomes C over epsilon naught times V minus IR but I is given by this thing right here. What does this all become? We get C over epsilon naught times V minus I naught E to the minus T over tau, and then we got to multiply that stuff by R. So now this is the flux through the capacitor as a function of time. Let's look at two extremes, okay? What is the flux at t equals 0? And flux we usually write as a phi. We'll call it phi sub E for electric field. What is the electric field flux at t equals 0? Well, we just plug in, let me erase this properly. We just plug in t equals 0 to this equation. And if I plug in t equals 0, what is e to the 0? It is 1. And so I just get the flux at t equals 0 is equal to C over epsilon naught times V minus I naught R. Okay. What about at very long times? As time increases and we go to infinity, what is the flux? If I put in t equals infinity there, e to the minus infinity is equal to 0. And so we just get C over epsilon naught times V. All of that other stuff goes away. Okay? That's pretty cool. Now, all right, if you want to calculate the current as a function of time, we showed you how to do it right here, right? I is equal to I naught e to the minus t over tau. So if you, for instance,